Hello, I'm Dean Gunnar from the Systems and Networking Research Group here at Microsoft Research Cambridge. And I'm going to demonstrate our research project called Wi-Fi-NC, or Wi-Fi Over Narrow Channels. So Wi-Fi as a technology works in a bit of the radio spectrum around the 2.4 gigahertz range. And each of your Wi-Fi channels, when you transmit to get internet access, takes about 20 megahertz. So that's a certain width of the spectrum that's used for each channel. Now, this works really well for Wi-Fi because in Wi-Fi we have quite a large amount of spectrum in one big long chunk. So you can have several people transmitting at the same time without sitting on top of each other and essentially reducing the amount of capacity they have. What's interesting about some of the new bits of radio spectrum that are becoming available is that we don't have the luxury of having a large chunk in one big block. We often have very much smaller chunks of bandwidth available. So for instance, in the UK, we've recently had something called digital switchover. So this is where the analog TV signal has been switched off and we're moving across to digital TV. And what's been left behind is little gaps in the spectrum, otherwise known as white spaces, where the TV signals used to be. And these gaps are typically much smaller than the 20 megahertz gaps that you have Wi-Fi. They're more like 5 megahertz or 8 megahertz chunks. So if we want to have the same kind of performance that we have with Wi-Fi for internet access in these newly available white spaces, then we have to be a little bit clever about how we use them. Otherwise we'll have to reduce our bandwidth. So what we do in Wi-Fi-NC is use multiple of these narrow channels, these narrower blocks, and combine them together or aggregate them to create the illusion to your PC or your mobile phone that you have the same bandwidth. That's exactly how Wi-Fi-NC works. It's the cleverness is in how we combine these multiple sub-channels into a larger channel as far as the PC is concerned. Now, the key challenge with doing this is if you have to use multiple smaller channels, they had to be packed closer together. You can't have a big gap between them. And in Wi-Fi, the gaps between these channels are typically 3 megahertz. But when we're using a 5 megahertz channel instead of a 20 megahertz channel in Wi-Fi-NC, we had to have a gap of no more than half megahertz. So that's what we can show here. In our demonstration here, we have a spectrum analyzer, which is essentially a piece of equipment showing the signal being transmitted by two radios. We have a signal from one radio here and another one here. What's worth observing is this whole bandwidth here is only 11 megahertz. So we've got two radios transmitting in two 5 megahertz chunks, and you can see they're really packed closely together. And if I take one of the antennas from one of the radios just to show what happens when you move the antenna away, you'll see that the signal goes up and down on the radio on the left. So you can see that signal goes down and it comes back up, but critically the signal for the radio on the right was not affected. I can do the same for the signal on the right. And again, it's not affecting the adjacent signal. And that's the key feature of Wi-Fi-NC. The other big advantage of using Wi-Fi-NC in these TV spectrum frequencies is that obviously TV signals go a very long distance. So it's a great opportunity to have a wireless internet access feature that can go much further than Wi-Fi can today in your house. So that's essentially how Wi-Fi-NC works, and we hope that this technology will be out in real devices in the next 5 to 10 years.